Hello everybody, I'd like to welcome you to my talk on statistical properties of syndrome Trellis coding. As at least some of you already have noticed, syndrome Trellis coding is a concept that we typically use in the context of steganography. And that's what we'll be talking about, even though we are currently in the slot for watermarking 2. Okay, in steganography by cover modification, we want to communicate a message M, and therefore we hide it within a cover object X. And this modified cover object containing the message will be then called steg object Y. This process can be divided into multiple sub-processes, and this was actually presented here in Magdeburg about 13 years ago by Jessica Friedrich. And we call the first process the encoding process, which tells us where we want to change our cover object, and the embedding process, the second process that just applies these changes. So connecting these two processes is the change vector C, just a binary vector telling us where we want to change our cover object X. Okay, as encoding is the main concern of our analysis, the focus will be on the change vector C, the binary change vector. But to make this a bit more complicated, we have another input to our encoding, and this input is called the change probability vector P. This change probability vector gives us the probability of each element of the change vector to be true. The idea is that we want to influence where we change our cover object, with the sense of changes at different positions having a different impact on the detectability of the changes. Just imagine we have a cover image like that, where we have a building and the sky above. A change within the sky, where we have just a gradient descent of colors, or even like a singular color, would be rather obvious, whereas a change within the twigs in the upper left corner or within the building isn't that obvious. To put numbers to this, we typically use cost heuristics, and these cost heuristics give us exactly that. Here presented with the bright yellow color in the upper right corner of the sky, meaning that there are rather high costs, and these bluish colors telling us there are low costs. And from these costs we can derive the change probabilities P. So these change probabilities are well defined. They don't come out of thin air, but we won't go into details how we derive them, as time is limited in this talk. Okay. So to solve this encoding problem, what we can do is we can use syndrome coding. And syndrome coding just presents this problem as a simple linear equation system, where we choose a coding matrix H, and we say, okay, the message M shall derive as a syndrome from this matrix multiplication of our coding matrix H with our steg object Y. So the problem with syndrome coding is just to find a change vector C that allows us to solve this problem. So there are a lot of ways to solve linear equation systems like that, and the result of it would be a sufficient solution in the sense that the message M is included in our steg object. However, the change vector might not fulfill these change probabilities. He probably won't fulfill them. So what we can do is use syndrome Trellis coding, where we have this syndrome coding as a condition, but also the idea that our change vector C shall be a likely realization of this distribution that we define with our probability vector P. Okay, so how do we do this in syndrome Trellis coding? Well, we define or we construct our coding matrix in a very particular manner, where we use the submatrix H hat and concatenate the submatrix again and again and again with itself, shifting it down a row each time we concatenate it. This specific construction allows us to use the Viteri algorithm, achieving these probabilities at the same time as solving the syndrome coding problem. So in the context of our linear equation system, it would look like that. Note the fact that the dimensions of our coding matrix are implicitly defined by the message length and the elements in our steg or cover object. So this is obviously just a toy example, because messages might be longer, and specifically steg or objects have more elements than just 20 pixels. So to answer our research question, how well syndrome Trellis coding does solve the problem of coding, we have to look at the change vector more specifically, and look at it if it follows the desired probability distribution. So we call this distribution a mutually independent multivariate Bernoulli distribution, just saying that each element of the change vector should be an independent Bernoulli experiment with a success rate according to our change probability vector P. So we will look at two selected aspects, the change frequency of individual pixels and pairwise independence in this talk. So let's start with the first one. What do? We embedded 50,000 messages on one cover of 64 by 64 pixels and compared the relative frequencies that we observed, like just counting how often the pixels changed to the desired probability. And yeah, we did this for 1,000 covers. Okay. Okay, let's draw this into our system model. We draw graphs, and on this graph we put on our x-axis the desired probability, and on the y-axis the observed relative frequency, and each pixel will be represented as a dot in this graph. So a dot above the main diagonal means this is a pixel that is changed more often than we would like it to be changed, and a pixel on the main diagonal representing a pixel that's exactly changed as often as we would like it to be changed. Okay, so here is such an example, and what you can see is there are a lot of dots around the main diagonal, so a lot of pixels are actually changed with a frequency similar to the desired probabilities. However, there are some significant outliers, and we wanted to understand why these outliers are there, and therefore we annotated these outliers with their position in the object. So remember, our cover objects were 64 by 64 pixels, so they have 4096 elements each, and these are rather small numbers compared to possibly numbers up to 4096. So they are all at the beginning of the object. And to understand why it is like that, we have to look at our coding matrix again. Because the coding matrix tells us how dependencies are formed. And here we see, okay, the first message bit depends only on the first 2 stego bits, whereas the message bit in the middle in our toy example depends on 6 stego bits. And there actually is the problem, this asymmetry. So let's go back to the first one. The first message bit depends on the first 2 stego bits. Let's assume the message is chosen uniformly randomly. Then the first 2, there's a 50%, at least 50% probability that one of the first 2 stego bits has to be changed, at least one of the first 2 stego bits, to fit this message bit M. And that's something that we actually observe. The problem is here that the desired probabilities of these two bits are much lower. Just because the costs were that high, that the desired probabilities are not that high. Okay, so the problem here is that with these 2 pixels together, we can't achieve the changes that we actually need to achieve due to the necessities of our coding matrix construction. And here we propose a modification. So this is how simple Trellis coding constructs this coding matrix, and the alternative that we propose as outlier corrected simple Trellis coding looks like that. And it is symmetric in the sense that each row of this coding matrix now contains each element of h hat exactly once. Remember, I told you that the coding matrix dimensions implicitly define the length of our message and of our cover object. And here we have a reduced message length. So for a fair relation or for a fair comparison between those two, we have to update this payload constraint by recalculating our desired probabilities based on the fact that our embedded message is actually a little bit smaller. Okay. What we can see here is an example of the example that we just saw. Now, also with outlier corrected simple Trellis coding, what we can see is that we were able to mitigate these outliers far above the main diagonal. Okay. So the second aspect I want to present to you is the pairwise independence, and for that again we embedded 50,000 messages in one cover of 64 by 64 pixels and calculated all the possible co-occurrences of pixel changes. Then we tested them for independence and repeated that for all the covers. So back to our drawing board, we have the change vectors. From the change vectors we calculate the co-occurrences. Based on these co-occurrences we do the chi-square test of independence. Note the null hypothesis is independence, so low p-values mean that we reject the null hypothesis, and thus low p-values mean that we assume dependence. Okay, we expect to see these dependencies close to the main diagonal in the sense that we expect to observe these dependencies at spatially close pixels, just because we have this linear construction of the coding matrix. Okay, to aggregate this, we calculate the ratio of low p-values in the sense that we just decide on a threshold of 5%. And then we just calculate the ratio of pixel pairs that has a p-value below this threshold. So we expect simple Trellis coding to include dependencies just because we have this fixed coding construction. And thus we expect to see a ratio above 0.05. So as we did this over all of our covers, we have 1,000 covers, so we have 1,000 ratios, and we represent these ratios here in histogram for all the covers. And what you can see is, well, our 0.05 would be the expectancy for the independent case, we obviously don't have that, we have this shift, and this proves the dependencies that we expected. So the interesting thing is that in case of syndrome Trellis coding, these dependencies are based on the coding matrix because it defines how dependencies are formed. More specifically, the submatrix H hat has a high influence on this too, because the coding matrix itself is constructed by the submatrix H hat. Okay, so let's sum it up. What we saw is that syndrome Trellis coding actually largely achieves the desired probabilities. However, there are some outliers, especially syndrome Trellis coding is prone to these outliers at the beginning of the cover object. Thus, we propose the outlier-corrected syndrome Trellis coding to avoid these outliers. There obviously needs to be more research, but this was our proposition for now. So, there is no immediate risk of attack based on our statistical analysis, just because of the fact that typically you use permutations to hide the order of the pixels. In a sound steganography setup, you would have a permutation for each element that you, or for each object that you communicate, a different permutation based on the key schedule or something like that. And this permutation is used before and after the encoding step, thus mixing up the positions during the encoding. So still we see a risk, or we have security concerns for the case of known or fixed permutation, because in case of a known permutation, an attacker would be able to use some kind of adaptive string analysis, focusing on the first few elements according to the permutation. And in case of a fixed permutation, an attacker, or at least a strong attacker, might be able to actually recover the permutation and then have the situation of the known permutation again. Okay. As a last note, research that is based on simulated encoding, as we often see it in case of comparing different cost heuristics with each other, this kind of research is likely not affected because they just use simulated encoding, meaning they use the assumption of perfect encoding and just do these Bernoulli experiments to create synthetical stego objects that do not actually include a desired message. Okay, so thank you for your attention. Are there any questions?